Thanks, everyone. So I'm going to talk a little about attention mechanism and how to use this in deep learning and how we can apply it in cybersecurity data analysis. So before we really dive into details, let's introduce what is the basic idea about attention mechanism. By language, attention means like you should focus on something rather than taking care of everything in your vision. So let's say in deep learning, there are always some study telling us like in the image there are some regions of interest that help you to categorize the content of the image. For example, if we say this image contains a dog, then the attention area should be the dog area. Otherwise, like you should focus on other things like human, cat, and other objects in the image, so that you can categorize this specific image into a specific category. So that's how attention, by its meaning, denotes. But actually, how attention mechanism was introduced into deep learning was from another perspective. It's from machine translation stuff. And the problem is like they're trying to fix the issue of processing really long text in machine translation. So I think that was like 6 years ago. There was a famous translation model named the SQL. That was like used two different LSTM or recurrent neural network to do translation from one language to another language. Let's say the example here. So on the left, we have the input text. The input text in one language, for example, they can be in English. We have a text here, and this is the input recurrent neural network. So this neural network is working as an encoder, which is transform all the language, all the words here in the input document into a low-dimensional hidden feature vectors. And these feature vectors will put into another recurrent neural network. This neural network on the right, they just work on the decoder of the language. So they receive the hidden feature vectors of the input sequence and generate the corresponding translated language text based on the input hidden feature vectors. So the two recurrent neural network encoder and decoder, they are chaining each other by the latent features of the input sequence. So this is the idea of SQL. Well, if you guys like ever apply this for like a time series analysis, you can also use this one to transfer say sequence of logs or sequence of security events into some feature vectors, and these feature vectors may correspond to class labels or other explanations about the security events. So SQL was used widely in machine translation and image recognition stuff. But there's a issue about the SQL model. So let's imagine we really have a long text here. So the input to the decoder recurrent neural network will be the very last hidden feature module that generated by the encoder LSTM, which means like every single input element of input sequence will first compress into this hidden feature, and this hidden feature will put into the decoder for generating the new sequence. So I would say like there are two issues here. So first, since like we compress everything into this hidden features as input, we might introduce many irrelevant information to generate a new sequence. For example, I wouldn't say like in a new sentence or new text, every word in the new sentence will correlate with the word in the original input sentence. I wouldn't say that. The word you always have some context information. So if you use all of the information from your input without any waste inside, and use this one as the output, as the input for the decoder, then you might be buzzed by some noisy information inside. That's the first issue. Second issue is like if one of the output elements of the sequence here is related with the input elements at the beginning of the input sequence. So the distance between the inputting distance is they are very far from the decoder sequence. So which is like the correlation between the input elements at the very beginning of the input sequence. They kind of like hold a very weak correlation between P itself and the decoded output sequences. So this weakened relationship is can sometimes harm the reconstruction performance of the output sequence. So that's another issue of this structure. So how we can handle this case? Just stuck with people for a while. I think in 2016, SQL method was proposed the first time, and then until like 2019, people begin to propose a new method try to handle this issue. So the solution to handle this issue is let's take an example here. So basic idea is the math like, for example, if we have an input sequence, how was your day? That was a English sentence here. And for each word, we just transfer each word into a word embedding. Like in our domain, like each input can be a security log. And for each log, we compress them into a feature. Let's call it embedding. Right? So this is the input embedding. And output is a French sentence, but it is the same thing. Comment se passe la journée? Okay, so each word of input sentence, each word input sentence, all of them, they will have some correlation with each word in the output sentence. But each word input sentence, they will play different roles in predicting the output word. For example, here like fast. I don't think like how and they will have a very close correlation with this word. Yeah, maybe was your, these two words will maybe just like was. This word just have very high correlation degree with this French word. So basically, this the observation shows us here like not every single input element they will hold physically strong correlation with the output elements in the sequence, but also like the correlation should be localized. So how we can present this localized correlation structure in the input sequence and output sequence, how we can make it learnable in the deep learning model. So that's a big question mark. And in 2019, people began to answer this question. And that's how attention mechanism comes out. So 2019, there's the first paper. They talk about like how we can try to adjust or present this localized correlation structure between the input sequence and output one. So how do we do this? So first, like for the input recurrent neural network, at each time step, you're going to have a hidden feature, or let's say this is the embedding of the current time step. So for example, this one input one, he will have one hidden features here, and for input two, he will have a corresponding input the hidden like embedding features here, and the input three they will have another input embedding features here. So usually, classically for SQL, what it has like they just use a very final embedding features as input to the decoder. But for attention mechanism, they use every single embedding features. They combine them together and put into the input of the decoder, which means like the decoder will receive not only the very last embeddings present the whole sequence, but also each of the embeddings present each of the input elements. So which means like the decoder has a better view over the input sequence. Every single element, I will know what where your embedding features look like. That's the basic idea. So if you look into that, actually we can see how they combine the embeddings of each input element. So let's say x1, x2, x3 until xt. They are the elements of input sequence from 1 to t. And for each of them, okay, we're going to have a embedding vector. Let's notice h1. So h1 is the embedding vectors of x1. h2 is the embedding vectors of x1 and x2. And h3 is the embedding vectors of x1, x2, and 3, and so on. So all of them will put together in a weighted sum way, so that we can give a different weight for different embedding vectors, and then we combine them together to give input into the decoder of the output sequence times step t. So here's like we can try to change the weight here, alpha t1, t2, t3 until tt here. We change the weight to present a different level of correlation between x1 and xt. Okay, for example, if x2, x3 has have the greatest correlation with st, then alpha t2 and alpha t3 they will be very large. Otherwise, like alpha t1, alpha tt, they will be very small. So in this way, we're trying to present the input and the output. They have some localized correlation structure. Okay, so this is the problem is like how we learn these parameters here. Alpha T1, T2, T3, TT. You can set it manually, but manually setting things cannot be reused for different cases. So you have to set these values as learnable values, and you should set up some learnable module to generate such a value. And this is called the attention mechanism module in deep learning. All right, so what do we have? Let's go back to the language example here. So how was your day? And then for each word, we're going to generate a word embedding here. Then let's say to the output of bus, this word will have another embedding. This embedding is something we want to generate. So the embedding of bus equal to the embedding of how was your day. You put together by a weighted sum form. So like alpha 0, alpha 1, alpha 2, alpha 3. They are the attention coefficients associated with each of the input word. And the alpha I, let's say this is we can simplify this case. Like alpha I is a positive value between 0 and 1. 1 means like you have a greatest impact over the output. Otherwise, our alpha I equal to 0 means like this word has no relation, has no impact over the output sequence, right? So these values will change the value, will change the alpha value. So the magnitude will help us to present which part of the input will correlate with the output. So that's the language example. Then how we can learn this example is like, for example, here we're going to, in the attention network, we're going to have first an encoder of your input. So input should be a sequence here. And in our case, in this case, it's a language. In our case, we can be say like, oh, this is a time series of security events like or API call sequence, right? So this is a sequence here. We use a recurrent neural network here as an encoder. And there should be some attention module in the middle. And this attention module is trying to learn for each of the output here. And you can have multiple output here, or you can have one single output here. Doesn't matter. But let's assume you have a multi-output which formulates a output sequence. So for each element of your output sequence, how to learn the correlation between your input sequence with this specific element. So the attention module here will take care of this job, which means like for each input, for each different output, for example, like st-1 here, you're going to generate a different bunch of attention parameters here. And for st, you're going to have different values for attention parameters. So these attention parameters are not set manually. So they are learned automatically. Try to adapt different input and different output. And then we're going to have another things like, okay, once we have the weighted combination of input features here, and then we're going to have a decoder, which is another recurrent neural network. We receive information from input sequence, and then we translate the input sequence into the output sequence, or just like output element, or just like class label. No. So these are three different basic modules of attention mechanism in deep learning. But the problem is like, okay, how we organize the learning of alpha. That comes to the problem. Okay. Here is a very general flow chart of how we're calculating the attention mechanism or attention parameters here. We'll have several steps, but let's go dive into each of the steps so that I can go through the whole flow chart. We understand how to generate such attention parameters. All right, so the first step I think this is quite normal. Well, you have like input sequence here, input 1, 2, 3, and then you generate, you go through the encoder recurrent neural network like this way. So at each time step, you're going to generate a embedding feature vector, and this embedding feature presents the information of all inputs until this time step. Right. So this feature vector presents feature input 1, and this one presents the input of 1, 2, and this one represents all the information, including 1, 2, 3. Right. So this is the first step. Let's generate the embedding features of input each time step of the input. All right. So let's assume. Okay. So this is two embedding features. One column is one embedding feature. So that means like these are the embedding features of two time step of the input sequence. So one column, one time step of input, and this is just like the input is the one time step of the output sequence. So just like one output sequence feature we put here. It's a one column here. And then you have two mapping layers here. They can be totally linear, they can be nonlinear. Doesn't really matter. But for a simple case, in the original paper, they're just using a full connected layer, so totally linear. So first, you transfer your embedding features of input sequence and output sequence. You map them into another feature space. Let's say you will just like, in PCA, you times one feature vector with a transformation parameter matrix. So you slightly rotate and make the transition, like a horizontal, vertical transition of your feature space. The goal is like, let's try to have a normalized, well-normalized feature space so that we can calculate distance between input and output feature space, feature vectors. Otherwise, since like the input, the encoder RN and the decoder recurrent neural network, there are two different neural networks. So basically, they generate two different feature space. You cannot compare them directly. So the mapping W decoder and W encoder here is trying to map the feature presentation from two different feature space into a common feature space. That's the use why we've set up two different transformation metrics here. And once you get the transformation of the output sequence feature and the input sequence feature here, so you can try to sum up that and take the tangent function to calculate what is the correlation between this output sequence feature and the two input sequence feature. But here, let's say this is not very straightforward. This sum up is like the column-wise sum up, which means like this output feature, embedding feature, will sum first one of the input feature here, like one time step, and this one will sum up again to the second column, which is the embedding features of another time step. So you sum up twice by each column, right? This is one of the ways you can calculate what is the correlation between this output feature and these two input features, but you can also calculate simply the cosine distance between these embedding features and these two embedding features as well. So you can choose many ways to do that. You can just take like a scale dot product, or you can just like take this cosine similarity, which ways you want, you can take that, because this is just like show what is the similarity between this output feature and the other input features. Okay. The use of the tangent function here is trying to normalize everything into a well-normalized value range. Otherwise, in the deep neural network, one of the big problems is like you have the gradient vanishing problem, the gradient exploding problem. So which means like you either have really large gradients somehow, and sometimes you can have really, really small vanishing gradient points, so that you cannot propagate your gradient back to your parameters. Then you got failure of your training process. And that's why I want to add some tangent function here, try to compress the value range between like -1 to 1 or 0 to 1. Okay. Here, this example uses tangent function, but you can use sigmoid function as well. The only use here is trying to compress the value range, right? And then the output is like for each column here, they record the distance between the input features and either of the output features. Sorry, the output features and either of the input features. Each column record that information. Then how we can transfer them into a score. I remember here we have each column here present the difference between the output feature and either of the input feature. And here we use another transformation matrix here. It's just to transform the column-wise difference into Q scores. So this is like a summarization problem or a polling problem. So by calling it polling, it's like you have, for example, you have two feature vectors. You make the difference, right? You make it directly the difference. Then you have the same dimensional vector to present. What is the element-wise difference between these two vectors? This is simple mathematical stuff. But the problem is like, can you summarize how different they are? Right? That is the following question. They differ greatly, or they have minor difference. No, we just need one summarized score. And this transformation here is trying to generate what is your summarized difference score between the either of the input feature vectors and output feature vectors. Okay, that's the use. For example, here, if you take that transformation, then you have one is 8, one is 9, which means like in each of the input feature vectors, the first one is closer to the output because you have 8 less than 9. Yeah, that's the only reason like we want to transfer the column-wise difference into a score-wise difference, right? So that is like polling or summarization step. So this is not enough because 8 and 9, you only have the ranking order 8 less than 9. But 8 doesn't mean anything. The magnitude 8 doesn't mean anything. Next time you might have like 10 or 100. Only the ranking order matters here. This is not good enough for deep learning, right? Because like each time you have different training samples put in your feature space or in your training pipeline, you cannot say like, well, we have some uncomparable magnitude value here, so that we cannot say we can use this magnitude value to generate some gradient to get our parameter calculation. So this is not enough for deep learning training. So how we do this? So we just take the softmax. Softmax is just like you trying to normalize each of the scores. Firstly, by taking I would say like 8, taking the division of 8 and the sum of 8 and 9. So which means like you just take the fraction of each of the score in the whole vectors. Then which vector will take the higher of a fraction in the sum, and this score will means like you have a better contribution or you have a more similar feature vectors between input and output, right? So this is just like the softmax here is trying to take the fraction number and use the fraction number is a similarity or distance metric between input features and one of the output features, right? So you take that one, and its value range is between 0 and 1. So here, not only the ranking order matters, like 0.73 is larger than 0.27, of course, but also all of the values, no matter which kind of score you generate originally, everything will be ranged between 0 and 1. So you have maximum 1. Means like you have absolutely greater contribution to the output. Otherwise, you have 0, means like you have 0 contribution to the output. So we take the normalization here. We have the similarity score or attention score that make a physically sense in the calculation. So that's softmax step. And that's not enough because we want to generate the context information of one of the output elements in the output sequence. So let's assume we have the attention scores for each of the input elements in the input sequence. And if we take the column-wise multiplication, so that first column will take the multiplication with 0.27, The second column, take another value like 0.73. So which means like, well, in these two input feature vectors, the first one will have less contribution to the output element. The second column, the second feature vector at another time step in the input sequence will have greater contribution to the output feature vector, right? So we just take the sum here, take the weighted sum here, then we get some context vector. Context vector is a summarization about all the contribution you might have from all the input elements with respect to one specific output element. So let's back to that language example. How was your day? And how each word, like how was your day, will generate value vectors here. And supposing here, like we're going to have 4 columns because each column corresponds to one word. And then you're going to have 4 scores. And each score corresponds to what is the contribution of the input word to the output word. Let's suppose the output word is journée. So this French word is closely related to day in English. So I would say like in that example, you have 4 columns here in English, and then the score will be 0, 0, 0, 0, 1, because only the last word day is correlated with the French word journée. So 0, 0, 0, 1, and then we take the sum, we take the multiplication and take the sum, then the context vector will present what will be the input information provided to translate the last word from day to journée. Okay, so this is called like a context vector. It summarize all information you can get from the input sequence, but weighted with their contribution. So this is the almost very last step of attention encoding. Okay, so once you have this kind of thing, okay, so we have the context vector here, which included all the information stuff here. And this is the embedding of previous decoder step. So like always remember, we're talking about time sequence. So you always have the embeddings from your previous time step in the output sequence, right? So like comment passe la journée. So comment se passe, they are the previous time steps. You should consider all of them will put first into embedding vectors, and this is the embedding vectors containing all information of the previous time step, but in the output sequence, right? So this is the decoder output. And the context vector, it comes from the encoder time series or time sequence information, right? So this is the encoder information. So this is the decoder information. And then this is the embeddings of current time step. So supposing like we are talking about journée, this word. So this is the fourth word. And this is the word embedding of the fourth word you can generate. So for this decoder, okay, so it's like the very last information combined with all the temporal information before this time step, all information in output sequence before this time step, and all information in the input time series or sequence, but weighted by the attention scores with this embedding vectors of this output time step. So you just like combine these 3 things together and put them into a decoder, like it can be LSTM, can be recurrent neural network. You put the 3 parts of the input and go through this decoder and just like transfer this information into another feature vector space and use a fully connected layer here and map this input into a classification or like machine translation output. So here can be, it can be do a prediction of logs. It can be one single word like journée here. Okay, so there can be one of the target you want to predict for this time step. And this is the how they chain them together. Like here, so for each time step, what you do is like, okay, let's first calculate what will be the context information of all the input, but weighted by the attention scores corresponding to each time step. So for each time step, you're going to generate first different set of attention values or attention parameters that try to calculate what's the correlation between the feature vectors of this time step in the output sequence and all of the elements in the input sequence. And for this, and once you get the context information, and also you get the information from your previous timestamp, you put them input, and you get the context information input, and you get your own information as input, and you get three-part input, you just get output. And output will be what will be my class label at this time step, what will be the correct word for this step. So you make the prediction based on all of this information. And then what you get is like, let me transfer my information again to the next step. And for the very next step, you do the same thing, right? You calculate again, what's the attention weights here? You calculate a new context vector. You combine all the information before you, and put all three parts together, and you get a new prediction output for this time step. So this is how decoder, RSTM, recurrent network, working with the attention mechanism here. So if you guys like feel interested, you can ever look into this paper, Neural Machine Translation by Joint Learning to align and translate. And this is, I think, the very detailed and self-contained paper explaining the first use of attention mechanism in machine translation. Right? So, of course, other people will propose environments, like environments to improve the attention mechanism. This is just like a cat-mouse game in the technical area. So what they do is like, all right, before that, the context information is only taken as the input of the decoder of each time step of output sequence. It's only the input for decoding things, and you can get an output from this time step. But in this paper, they're trying to introduce like we use the context vector directly as another output, another input to decoding, to combine with the decoding prediction again. So here you might have a linear combination here. So which means like the output from each decoder, not only the prediction output, but also contain what is the context information from your input. There's no explanation why it's better, but this is just like deep learning, you know. You add more links here, you get you get more information, and theoretically you will have better classification or translation accuracy. That's how deep learning works, I would say. But I think I can find some possible explanations. Like, you know, like in deep learning, it's like you have more and more layers, then your gradient will disappear somehow at some point. And you say like, okay, I cannot propagate my information from previous layer parameters to the layers at the very bottom. So the layers at the bottom, they will stay randomized. They randomize initialize, then during training, they stay randomized because the gradients are approaching zero. So somehow they will use some ResNet skill, like we use some skip link. We jump from the very beginning layer directly to the very last layer. So that way, like we can transfer our gradient from this skip link directly to the deeper layers, so that we can try to push them to move along the optimization path, and somehow they can work and try to update the deeper layers efficiently. And this is the skipnet technique in ResNet, and this is very similar with the ResNet stuff. So okay, here the decoder hidden state. This is not just like one linear layer. It can have several layers here. Then it's possible like the context information passing through several layers. The gradient of the context vector will vanish somehow at some point based on the database distribution. So they add some skip link directly from the context vector here, passing through the skipping through the decoders directly into the prediction output. So that's why like trying to give more context information about the input to the prediction output directly. So somehow if the context information change, we have a gradient over the context. This gradient over context will be directly presented in the prediction output. So that's one way we might be able to train this super complex deep learning neural networks more efficient. That's my explanation about that. I never did any experimental study, but we can try to understand from this perspective. All right, so again, if you guys feel interested about that, you can read the paper's effective approaches to attention-based neural machine translation. So this is the second paper about how we use attention mechanism in machine translation. Until now, we're still talking something about sequel to sequel, which means like we try to do the mapping from one sequence to another sequence. This is useful for machine translation, but for us, like for cybersecurity or even for computer vision, this is not very interesting because for computer vision, for cybersecurity, we always want to do detection, classification, so output should be one single element. So how can we do that? All right, so this is one of the extension of attention mechanism here in the different data structures. So people can try to present things in the graph. One of the examples, you can present how a software works by using the control flow graph. You start from one entry, it goes through some API calls and some resource access, and you reach some termination point. So this graph will show the logic inside a software, and also you can have network traffic. I think some of you just quite familiar with that part. I don't want to repeat that again, or you can correct me if I'm wrong. So you just link different IP together, and which IP send which message to which device, which hosting stuff, which destination stuff, and the whole graph will present a security event or security instance within a time period, and that graph structure will tell you everything about how these things happens inside. So if we use those graphs as input, the output will always be, if this graph presents a malware or denialware or intrusion detection or totally denied traffic. Okay, so this is just like a classification output. You only have one single element as output. And one thing we can do this is trying to use graph neural network. And the thing's pretty straightforward. It's like for each node, well, you might have some information for this node. For example, this node may present a specific API call or some specific memory address, right? So they can be, they can contain some attributes. Of course, for network traffic, this node may contain, maybe this one is a connection log. Then it will contain like a number of packages sent, IP address, port protocol. A lot of information will contain in this node. So the link represents the this direction is like how the information sent from this node to this node, or the control flow goes from this node to this node. So we use firstly some locally functional mapping here. Maybe like this is a 2 or 3 layers of neural network. We transfer the input features, the raw features, into some computable embedding space. And then we send these embedding features from this node to the neighboring nodes, because your neighbors want to know what you're looking like. So that you collect the information from your neighbor nodes and sum up with your own features together, and you go through some filtering again. So you get not only your own attributes, but also the attributes from all of your neighbors. And through this way, we're trying to present trying to summarize the information. Or topological information within a very small neighborhood around one node. And this iteration step, this is information collection and propagation step, will be iterated within the graph structure again and again and again until everything got converged. Once you converge, you can say like, okay, I got the feature vectors of each of the node. And these feature vectors will be used to do classification, say, want to classify this connection log corresponding to malicious or denied traffic. This is binary stuff. So this is how graph neural network can be used in our case, right? But this case, like you can even like we sum up, we stack all the node embedding vectors into a global embedding vectors, and this global embedding vectors present the whole graph instead of presenting one single node. You present the whole graph. And the points like we can compare the similarity between two graphs. It's possible like two graphs present two different logics of running things. So you compare the similarity to graph, you might be able to grouping different malware families together. And one is one of the examples. Right? So this is the basic way we can use the sequence as input, but one element as output. If you imagine like in the graph structure many, so each of the paths traversing your graph will be a time sequence. And input in a graph neural network will be several or possible random walk paths of your graph neural network. So you have different time series as input, and output is just one, just like the embedding of one node or embedding of the whole graph. All right. So that's the graph neural network. Since the input is a sequence, is a random walk path, we can generate a graph attention mechanism network here. So how we do this? It's very straightforward now. So for the graph neural network, let's say this is the central node. You want to generate some embedding vectors. What you do is like all of his neighbors will send information to him, send the embedding feature to node attributes to him, so that we can make some locally mapping or transformation here. So instead of treating every neighbors equally, we put a value here, we put a weight here, trying to weight what is the contribution or similarity or affinity between this central node and the neighbor node here. One example is like in social network, you always have some impactful users, like he's a harbor user. Everyone just connected him and he just wants to show a lot of interesting things that people just share, right? So this node will have a greater contribution to everyone connected to him. So some guys like you link to somebody just never say anything, never post anything, so you have very little contribution to the people around you. So those kind of stuff, those kind of contribution is weighted by these parameters, and these parameters will be called a graph attention parameters. And this is again, this is a learnable. There's a trying to automatically measure. If I give you a new graph and I point out one single node here, can you tell me what will be the contribution of your neighbors to this central node, or what will be the correlation between your neighborhood with this node? So this is a directly extension of the graph neural network by using attention network here. You can imagine like this, just like a attention module plus a graph neural network, and attention mechanism here is just like a plugin module. All right, so we have a vista here. So this is the latest variant of attention mechanism. It's called a transformer. Definitely, it's not this transformer. So it's actually more complex than a single module, like you generate what is the correlation scores or correlation parameters between input features and output features. It's more than that. They have several layers of attention stack here. So here, like we have several encoder. Let's say the input is still a sequence. The output can be a sequence, can be a one single element. Right? So the input sequence will go through several layers of encoder, and each encoder layer will have a attention mechanism here. You can imagine this is just like a information squeezing process, right? So that the first step, let's say this will measure what will be the correlation between the input sequence and output features. Okay, right? We squeeze this by the word level information, and somehow like you can treat the output from the first encode layer is the semantic topic information about the input sequence. So for example, you can imagine you can take this one like the combination of different words together, and combination of different words with corresponding to different semantic topic, and the topic will present as the output from this encode layer. And attention here is like trying to give different weights to different words in the input, and try to accurately capture the topic inside the input sequence, input text. Well, the second encode layer here is trying to squeeze that information again, because the grammar information or the semantic information can be hierarchical. Like you can have really local view over one node, one word, and two neighbors beside this word, right? This is a very local area. you generate some attention here, you put your attention here. But maybe this part, these 3 words, can be correlated with another 3 words in another place in your text. But this is quite distant. You cannot use the one attention mechanism to handle all of the correlation. So what you do is like, let's focus on the localized area. Let's focus on the local correlation in a very small neighborhood at first. This is the first layer. They do the job like this. The second layer is like, once we abstract the information from local area, then we can try to link different local areas together by using the attention mechanism. So this is the second layer. They do the same job. So eventually, by passing through several encoded layers, you just like squeezing until you reach the capture, the semantic explanation of the whole sentence. The sentence could be really long, can be really a large document, but through this way you can just compress the whole document again until you reach some very compact presentation of the semantic meaning inside this document. So it's more or less like if we really have a huge image, let's say we have a really huge image, like satellite image, can be really large. What you do is like, I can do filtering directly on this image, but this can be really time consuming. So what I do is like, okay, I just like using sliding window from beginning to tail, I just generate several millions of filtering response. So what I get is like a real. I get my first kind of information about this image, but it's really expensive to get, and it's really difficult to analyze because I have really high dimensional space to handle. So instead of doing that, what you can do is like, okay, let's just focus on the leftmost area of this image. Let's do the analysis of this one and try to get what is the content in the leftmost corner and rightmost corner and the other corners of the image. Right? Once I get the information about different area of this image, and then I combine the information of different images together. So this is lower dimensional space, and I squeeze them again, try to enlarge my analysis view over a wider space, subspace in the image contents. So this way, like we combine local information together until we reach a holistic understanding about the image content. This is a hierarchical process of understanding what is the contents inside the input, instead of like we're doing brute force way of filtering or feature extraction over a really large space, really large feature space in the input. So again, since we have several layers of the encoder, we're going to have several layers of decoder. The reason is like it's similar. Like you can always use like one single decoder to map the feature to another very large, very high dimensional output space. Supposing we are doing feature translation, then you have maybe 1,000 words in input. So your output translated words shouldn't be like only 1 word or 2 words. It should be a long text as well. So for this, in this case, like you cannot use one single decoder to project low dimensional space directly to very high dimensional output. This is very difficult. Otherwise, you're going to have some cursive dimensionality issue in model fitting. So what you do is like, let's put several layers decoder one by one, so that we can gradually to decoding the information compressed in the output from the encoder. So that's the way like we follow the divide and conquer scheme. Try to split your difficult problem into easier to handle sub-problems, and try to solve each sub-problem one by one until I reach my answer of the final problem. So that's the basic idea of transformer. And until now, I mean, transformer now is the, how to say, can be the baseline of deep neural network in computer vision and machine translation. So everybody, if you want to publish a paper, you should use this technique. Otherwise, like a reviewer gave a no to your paper. Okay, so back to our case. What is the impact of attention mechanism to cybersecurity practices? So I want to use one paper as an example. So this paper is a deep case, assignment supervised contextual analysis of security events. And I put the link here. If you guys are very interested, you can search the paper and download it. So the basic use case in this paper is like, supposing we have a system log-based network security monitor. This monitor is like collecting the logs of security events. The events can be benign, can be malicious. We're just collecting them with a timestamp. So at timestamp 1, I observe this log, and timestamp 2, I observe another log. So the log can be like repeated SSH login attempt. So repeated SSH login attempt, they can be totally benign because I forgot my password. So I tried again. So you have like an observed like a malware signature. This is malicious. So you see here, logs can be benign, can be malicious. The only thing matters like the combination of logs. Like you put several logs in the time series, and this time series of logs, they mean something. So I will dive into the example. So once you dive into this database will give you different time series of logs. They can be different lengths, right? You can long, you can short for each session of execution. You can have 100 logs for one session. Maybe you have like only 3 logs for one session, another session. All right, so you have different time series of the logs. And then what this deep case do is like, okay, supposing we observe in a session like we have E1, E2, E3, E4, and they are the 4 logs at 4 different timestamps. What they do is like, okay, given this observation, can we make our prediction? What will be the next system log look like? So this is the prediction task, trying to prediction what will be the next logs. And this model is trained on the normal sessions. And there's no abnormal behavior. There's no malicious incident inside. So we learn how logs evolve in this system. And once we manage to do that, then you can make the prediction on next log. Say, normally, if there's no malicious stuff, if I have E1, E2, E3, E4 is input, so E5 will be my next log. And this forms a normal behavior. And if we predict something that is different from what we observe, and this will be a abnormal behavior because you just deviated from normal log sequence patterns. So that's the logic of deep case-based anomaly detection. So you predict what will be the normal evaluation or normal evolution patterns of logs. And once your prediction is different from what you observe, and this will be anomaly stuff. And this is the idea. So for this method, what we do is like first, let's use recurrent neural network because this is time series. So let's say for each of the log, you can treat each log as a word in our word, in our research domain. So E1 is a word, E2 is a word, and E6 is a word. You have 6 words as your observation. What we do is like let's predict what will be the next log here. So actually, you just build a recurrent neural network. First, you put the word embeddings of each of the log here. Put the embedding here as the input of your recurrent neural network. And the recurrent neural network just memorize what will be the patterns of from E1 to this one. Okay. And normally, what is the pattern will be looking like in learned by the LSTM or recurrent neural network here. And when you use that, you say like, okay, I observe E1 until E6, and what will be E7? What will be the log that happens at E7? So the LSTM here will try to predict the very last step, what is the log at the very last step. And since here is like just like simple recurrent neural network log, but here we're just trying to add the attention weights to different logs here. Because you might have really long system log observations. You might have 100. I'm sure like at the beginning, maybe the log at the beginning, they have really weak correlation between with the log at the very bottom. So you don't need to treat each of the logs equally in your prediction of future logs. What you can do is like I just put attention here, just like put different attention parameters here to E1, E2, E3, and E6. And then once I do prediction, so they will show like some logs, normally some logs will have a great correlation with the E7. So this log will have great attention values. Otherwise, some logs will have very weak correlation with E7. So this log will have really low attention stuff. So using the attention stuff, we can try to focus on the local correlation between the logs, and they help us to actually capture. So first, what will be the prediction output? Secondly, what will be the anomaly behavior deviated from normal log patterns. So that's basically used for attention here. But another things like we can make use of attention mechanism in deep case, like once we learn the attention parameters for different log patterns, and this attention values themselves, they can present different correlation between different normal behaviors. Like maybe for some normal behaviors, like the attention values for E2, E3, E4, they are high, but the E5, E6, they're very weak. They can hold a very low correlation with E7. For the others, maybe like a E1 and the E5, they're higher, and for the other logs, they were very weak stuff. So the distribution, the different distribution of attention weights here, or attention score here, they present different patterns in your normal behavior. And these attention values will help us to grouping the time series of logs into different clusters. So in that way, like you try to do clustering of system logs and put it into different clusters by using the clustering over the attention weights here. We can put the different series of logs put into different clusters, and each cluster they share very similar correlation structure between logs, and also they share similar temporal patterns of logs as well. So they give a very strong constraint within each cluster. The system logs will share high similarity between each other in profile. And this will be taken as a context or typical system equation traces. And these clusters will store in the database. And once we have a new thing, once we have a new time series of logs come in, and we calculate what's attention values, and we do clustering here. So we can first to compare if this new series of logs belong to any of the clusters we store in our database. If this belongs to any of them, so we can categorize them the specific behavior. So they can have, for example, if we're talking about a different attack behavior like bottleneck behavior, so you will have different clusters of bottleneck technique. Then if you have a new things coming, you want to decide whether this is a already known attack behavior or not, or something we don't have any idea about that, right? So if this belongs to this cluster, we just categorize them. Otherwise, if this one stay far from any of the clusters in our database, means like either this is like this is normal stuff, this is like concept drift, our system settings change, so our behavior change. Or this is zero-day stuff. People use new technology to compromise our system. So from data mining stuff, this is outlier. And the outlier may mean some interesting things. And the existing outlier will invite human experts to look into, specifically to this new stuff, and trying to trying to collect information to help machine learning systems to return. For example, well, if this is outlier, we know nothing about that. If this is outlier, and we have human expert come in to investigate this outlier, and they found, okay, this is a new technology, new attack technology here. So we can put a label here. Okay, this is another attack here. And from now on, we can try to collect more information, more data according to this new attack. And this will be the base to retrain our attacker, like our attack detection model. Or like say humans say, well, this is a new things, and this is stay away from each other. And if human experts say, oh, this is totally normal, this is benign, that means like system settings change. There is a behavior concept drift inside our data mining. So it's possible like we need to retrain our classifier to adapt to this concept drift. Otherwise, like people will say, human expert will say, well, the feature used before, some of the features, they're not usable anymore. Some of the feature space you need to change. And the machine learning system will update the feature space change. And then we can retrain our classifier using the new feature space. So in any of the cases, clustering using attention values of the system log series will be the core technology here to set up a bridge between the machine learning staff and the human experts. And human experts here trying to give you feedback to enrich your technology in your machine learning training base so that you can update your machine learning model. And from machine learning side, it's like trying to filter out most of the really relevant or not interesting data So you can say like every day we will receive billions of attack records in future. Possible, like we set up some service and open to outside, we can receive a lot of attack incidents every day. But I would say like most of them, they are not interesting. They are, so first they can be random attack. They can use like very old attack technology. People just want to try, right? So this incident are totally irrelevant and totally not interesting. We cannot let human experts sitting here and looking into every single of them all day. So we just like using machine learning as a filter out most of the irrelevant cases and just pick out those outliers quite interesting to people and let human experts focus on those stuff and invest them and give us the interesting feedback and try to refine our machine learning model. Somehow we call it like a human-centric machine learning for cybersecurity practices. Okay, so finally for takeaways, attention mechanism here, I would say the core idea of attention mechanism is trying to evaluate for a given output, what will be the correlation between your training data. First, what will be the training features, correlation between training features and one element of your output. For example, if your output is sequence, then pick up one element in your output sequence. So what will be the correlation between this element and your training features in the database? Okay, so this is the first layer, attention. Next layer of attention is like, okay, so now we're putting machine learning into practice. The input is a sequence, the output will be an element or multiple elements. So what will be the correlation between the input testing features and your output? Your output can be classification output, so it can be class label. So which of your input features is correlated with the classification decision output? So this is want to generate more expandable decision in machine learning model. Not only give you a score, telling you, oh, this is malicious, and give you a score like 0.68. I don't really care. What I do care is like which features trigger your decision. Why you say this is malicious? Why you say this is benign? So from attention values, we can evaluate what will be the contribution of each input testing features. We can pick out those testing features with very high attention value, and these features explain why you make this decision. And when we bring them together, we can try to check them and let human experts check them, why these features explain the existence of this malware or the existence of this technology, or we make something wrong. This is totally like a statistical overfitting. So attention values give us this chance to explain that. And also, by using the attention mechanism here, like the training data, when you organize training data, what you do is like I try to collect as much as possible information. I don't really care. Like I just like collect whatever I can get from the system. You might have a lot of irrelevant information. You might have a lot of noisy information, especially once you do some industrial cases. So attention mechanism here is trying to automatically remove the impact of those irrelevant stuff, because those irrelevant stuff, they have low relations with your low correlations with your output. So attention values for these irrelevant values will be very low. And for noisy stuff as well, normally the noisy stuff is like totally random. So you might hold some strong correlation somehow at some point, but you might have like a low correlation at the other points because the noise corruption is random. And then in this case, like if you take an average, the attention value of this feature will be very low because once you sum up the very high value or very low value, the average will be very low. That's the intuitive. But for attention values, like if the contribution of this feature is not stable, your attention value will be very low on statistical sense. So that's the third point. Like we can make use of attention mechanism, try to remove the noise, the impact of noise. So again, back to cybersecurity research, right? So what you do is like you want an expandable or interpretable decision output. So using attention mechanism here can help us to try to capture what is the impactful factors. And the combination of these impactful factors, they show the signature of specific security instance. Like in future, maybe you want to use dynamic traces to do classification, family classification. When what you do is like, okay, which part of the dynamic traces they correspond to the payloads? We don't know. We can let human experts, we definitely can let human experts look into each of the traces and try to locate, well, this is part of the codes, this is part of the API calls, the corresponding payloads. That takes a lot of time, right? We cannot do that. So the machine do that, it's like, if we put the attention mechanism here, we can try to evaluate if this traces corresponding to the malicious family, and then which part of the dynamic traces they have a great attention values or greater attention values compared to the other dynamic calls, dynamic API calls. And this part of the dynamic API calls, they have a strong correlation with your malicious output decision. And this part might be the part of the payload, the malicious payload, that you should look into. So attention mechanism here, trying to filtering out most of the irrelevant information, help us to focus on real, the parts like holds strong correlation with your output. And then from that part, they give you a strong hints, like which part of the input you should look into and try to get some knowledge from that. So I think that's one of the possible use cases that we can apply in our cybersecurity practices. All right, okay, thanks for your attention. If you have any question, please feel free to shoot.